Hello and welcome to Honors Function. This is the last lecture on exponential function. In this lecture, we're going to cover one of the most important property of exponential function. Actually, let me rephrase that. We're going to cover the most important property of exponential function. Let's begin this lecture with a sentence that I picked up from Wikipedia at the article on exponential function. So let's pay attention to the sentence, shall we? The exponential function is used to model a relationship in which a constant change in the independent variable gives the same proportional change, percentage increase or percentage decrease, in the dependent variable. So if the input, that's an independent variable, if the input changes at a constant pace, meaning you go from x to, I don't know, it doesn't matter, right? X plus d, and then x plus 2d, and then x plus 3d, right? Then the output, the dependent variable, will change at the same proportional change. This is the relative rate of change, something we defined, I believe it was in lecture 23 or 24, the relative rate of change, okay? And there lies the quintessential property of an exponential function. Let's try to understand that. So to understand it, I'm going to take an exponential function base a right here. And we know that a has to be positive, right? Okay. So I'm going to look at the relative rate of change when the input increases by 1 unit. So from x, I go to x plus 1. Okay. Let's check out the relative rate of change, shall we? F of x plus 1 minus f of x. Now, this is called the total difference, you remember? Divided by, now, not x plus 1 minus x, that would be the average rate of change, but divided by the original output, f of x, okay? What is this? This is f naught times a to the x plus 1 minus f naught times a to the x divided by f naught times a to the x. Okay, so what is this equal to? So this is equal to 2. So let me factor f naught times a to the x, okay? Now, times what? Times a, all right, minus 1, okay, divided by f naught times a to the x, right? If you distribute this, you will fall back on this right there, right? So you can simplify by this, and you find a minus 1. What the heck does this mean? This is not a function of x, right? It doesn't matter if x goes from 1 to 2, okay? It doesn't matter if x goes from 1 to 2, or if it goes from 1000 to 1001, or from 1 million to 1,000,001. The relative change, okay, this ratio right here will always be equal to a minus 1. If you call this r, right, if you set a minus 1 equals to r, then this is the relative rate of change, and you can read it in percent. Now, that should remind you of something we covered in the previous video, right? If a minus 1 is r, then that means that a is 1 plus r. Now, what did we go over in the previous video? Let's check out these notes again. Now, you see the formula right here? This is your a, right? And this is the what we call the interest rate. What I'm actually saying in this video, I'm actually saying that any function, any exponential function, can be viewed as a model of growth and decay. A is 1 plus r. If r is positive, you got growth. If r is negative, you got decay, right? Here you got growth right there. And here you got decay, something that decreases, right? It means if r is negative, a is smaller than 1, right? And if r is negative, and if r is positive, a is greater than 1. And we know this is growth and this is decay. Let's go over the first example right now. So here is the first example. Find the expression of the exponential function whose characteristic is given below. So here's the initial value. So this is f0, right? f0 equals 125. And it decreases at the rate of 20%. So r is negative 0.2, 20% decrease right there, okay? Every 1 unit, okay, that's really important, every 1 unit. And so what's a function? So f of x is equal to 125 times 0.8 to the x. That's it. I got here is, right here, it is 1 minus 0.2. That's it. This function describes a decrease of 20% every 1 unit. All right? I'm going to let you do number 2 and I'm going to do number 3. Number 3, f of 2 equals 49 and it increases by a factor. Be careful here. It's a factor. It's not a rate of 175. So the factor is a, right? That's what we call the factor. So do not confuse factor and rate. The rate is r, right? The factor is a. Why is the factor a? Why do we call it a factor? Because if you do f of x plus 1 divided by f of x, okay, this is just f0 times ax plus 1 divided by f0 times a to the x. Well, this is just a, right? So you have f of x plus 1 equals a times f of x. So as x increases by 1 unit, the output gets multiplied by a all the time. Again, not a function of x, a constant thing. It increases by a factor of a. And a is 1 plus r. So if it increases by a factor of a, it means the relative change between f of x and f of x plus 1 is r%. Okay, again, don't confuse factor with relative change. All right, so let's go back to our question. So here, f of 2 equals 49, and it increases by a factor of 1.75 every 1 unit. All right, so what can I write? I can write f of x equals, I don't know f0, right? f0 times 1.75, that's my a, to the x, okay, every 1 unit. So how do I find f0? Well, what do I know? I know that f of 2 equals 49, right? So what does that mean? It means that f0 times 1.75 to the second power equals 49. And so f0 equals 49 divided by 1.75 to the second power. So I'm not going to take my calculator here. I can just rewrite my function. I have it. F of x would be then f0. So 49 divided by 1.75 to the second power times 1.75 to the x. And so what is this? Oops, sorry, I'm getting a little bit right here. So this is f of x equals 49 times 1.75 to the x minus 2. That's it. If I'm given a value that is not, this is not the initial value, right? Not the initial value. I can always find an expression of my function. I will have to shift my graph to the right. That's a translation 2 units to the right. So it's like if the graph started 2 units to the right, right? Okay, let's go over the second type of examples. All right. What is the percent of change per unit of input? Okay, so when you go from x to x plus 1 for the following exponential function, specify increase or decrease. Okay, so here's my function. So what is a here? A is 2 and 2 is 1 plus 1. So this is 100%, right? 1 is 100% and so r is 100%. So this is a 100% increase every 1 unit. Okay, basically you double every 1 unit. It makes sense right here, these two. I'm going to let you do number 5. Let me do the last one, number 6. So number 6, so what is a? A is 1.055 and this is supposed to be 1 plus r, right? So if you subtract 1 to that, you find r equals 0.055, which is again 5.5 5% divided by 100, right? And so this function describes an increase at the rate of 5.5% every 1 unit. All right, this is very important, every 1 unit. Now let's see what happens when it's not every 1 unit. Let's go over example number 7. So what's going on here? The initial value is 125. The rate of decrease is 20%, but now it's every 3 units. Every 3 units, you get a decrease of 20%. So if you write f of x equals 125 times 0.8 to the x. Now you do have r equals negative 0.2, right? So it's 20% decrease. That's what it means, a negative sign, right? We do have our decrease of 20%, but the decrease happens every 1 unit, right? If you do f of x plus 1, it's going to be the same as f of x times 0.8, right? So you decrease by 20% for 1 unit. We don't want it to happen every 1 unit. We want it to happen every 3 units. So how can you change this so it happens every 3 units? Check it out. It is not very difficult. This is what you do. You just divide that input by 3. Why does it work this way? Here's the proof of it. F of x plus 3 has to be the same as 80% of f of x, right? This is a 20% decrease of f of x. Let's check that this is true. Do we have this? If I do this, absolutely. Look, f of x plus 3 is equal to 125 times what? Times x plus 3 divided by 3, right? Okay, so what is that? This is 125 times, oh, I forgot my 0.8, sorry. 0.8 to the power of, so x over 3 plus 1, right? This is, I'm breaking this fraction, right? So what is this? This is 125 times 0.8 to the power of x over 3 times 0.8, right, to the first power, but I don't write the first power right here. I'm using the rule of exponent. Now this is all a product, so I can rewrite it as 125 times 0.8 to the x over 3 times 0.8. And what is this? This is f of x. So it's f of x times 0.8, which is a decrease of 20% from f of x. And that happens every 3 units, not every 1 unit. This is what you do. Very, very simple. Let's go over the next example. So here, the initial value is 0.05, and the increase is 1.05% every 2 units. So check it out. Very easy, right? So initial value, 0.05 times, okay, this is an increase, right? So it's 1 plus, so it's 1 point, and it's R is 0.01%, so 0.0105, right? No, that's one too many zeros. Sorry about that. So here we go. This is 0.105. That's it. Right here, you get your 1.05%, right? Here we go. That's my R. And how do you specify an increase every 2 units to the power of x? Now, x over 2. Right? If you just have to the power of x, this is every 1 unit. You want every 2 units, just divide x by 2. And that's how you get every 2 units. Okay? Very simple. And of course, now that we have every 2 units, every 3 units, every 5 units, every 10 units, we could also do every 1/2 units, right? So if it is 1/2 units, you divide by x to the 1/2, which is 2x. If it is 1/10 unit, you divide by x to the 1/10, which is 10x. Well, what about if it is not just every 1/10 of a unit? What about if it is all the time? What about if it is the continuous model? We've seen what happened to the continuous model, right? What happened if you have a continuous model? F of x is f naught times e to the rx. We've seen that again in the previous set of notes. So if it is continuously, then the base becomes e. All right. So we're going to finish this lesson by comparing rate of increase. Let's check out the question. So here we go. I want to compare an increase of 20% every 4 units with an increase of 14.8% every 3 units, with an increase of 9.65% every 2 units, 4.72% every unit, and 4.6% continuously. You see, so I'm decreasing my units to every 4, every 3, every 2, every 1, all the time. Which one do you think is better? Okay, so here's what you're not supposed to do. 20% every 4 units means divided by 4, and that's 5% every unit. This is completely not true because you're dealing with an exponential function, okay? You're applying something very linear here. You think if you got a 5% increase every unit, you're gonna get a 20% increase every 4 units? No. If you got a 5% increase every unit, you're gonna get above 20% increase every 4 units, way above, right? So what's the equivalent per unit of a 20% increase every 4 units? It's very simple to do. Check it out. So how do you model 20% every 4 units? Very simply. F of x would be, well, the original amount, which I don't know what it is, but it doesn't matter in this problem, times 1.2, right? 20% increase, it's an increase after all, every 4 units, x over 4. And what is the equivalent per unit increase? Well, you know, if you have a per unit increase, then f of x has to be equal to f of f naught times a to the x, right? This is where you see your frequency of increase right here, x over 1 per 1 unit, right? And so how can you go from here to there? Very simply, check it out. F naught times 1.2 to the power of 1/4 to the x, right? And so a, in this case, would be 1.2 to the power of 1/4. Okay, so 20% increase every 4 units correspond to whatever that is. Be careful, it's a, right? So I need r. So r is a minus 1. So you need to subtract 1 to that. And that is the per unit equivalent to 20% every 4 units. All right? So let's take the calculator at this point and let's figure out what this number is. All right, so 1.2 to the power of 1 divided by 4, so that's 0.25. And then minus 1. So what is this? This is 4.66%. Here we go. 4.66%. So 20% actually, you know what I'm going to do right here? I'm going to erase all of that right here. I'm going to erase all of that. And I need to keep track of what I'm doing right here, and it's a bit messy. So 20% every 4 units, right? Every 4 units corresponds to 4.66% per unit. That's what it corresponds to. Okay, so now what is 14.8% every 3 units? So let's do the same right here. Let's transform this in a per unit frequency. All right, I'll do it a little bit faster. So what would be the function that models a 14.8% every 3 units? It is f of x equals f naught times, so it's an increase, so it's 1.148 to the x over 3, right? And this is the same as f naught times, so 1.148 to the 1/3 to the x right here, right? And so in this case, a is 1.148 to the 1/3. And so if you now want r, just subtract 1 to that. Okay, let's check out this number. So 1.148 power 1/3, 1 divided by 3. And let's subtract 1. This is a factor. Let's subtract 1 to get the rate. So it is 4.71 about, right? 4708. So that's 4.71%. So we got, this is about, so the second one right here. So 14.8% blah, blah, blah corresponds to 4.71% per unit. So now I can compare. And I know that at least between the first two, the second one is better. I prefer this one. I prefer 14.8% every 3 units, to 20% every 4 units. What about this one? It's the same thing. So, okay, let's do it one more time, and I'm gonna let you finish this problem, okay? So here, we would have f of x equals, so original amount times, so 1.0965, here we go, this is a 9.65%, but it's every 2 units, so x over 2. So a simple rewriting is going to allow us to find the, I was going to say yearly. It's per unit. Of course, it's usually yearly, right? It's usually, these models are very common in finance, and it's usually a yearly increase, but it doesn't have to be yearly, right? So that's why I'm sticking to per unit. So 1.0965 to the 1/2 means square root, okay, to the power of x. And so if you want r is 1.0965 to the 1/2 minus 1. I want r, right? Not just a factor. So let's take our calculator and let's do 1.0965 power 1/2, so 0.5 minus 1. All right, let's see. And here we have, so, we have to be careful right here. It is 4.71%, but you see, this one is better than this one because it is 713, while the previous one was 708, okay? So again, if you just look at the approximation to the 100, it would be about 4.71%, and then you would say, oh, well, they're the same, but actually you know that this one is a little bit better. Please finish this problem, especially for the continuous rate. I'm going to let you figure out it's exactly the same thing, right? And thank you for watching.